Okay, hi everyone. So today is your project presentation day. So we have first presenter, India. So she's going to present her research progress, which is about applications of graph theory for Markov chain. And how do you pronounce this? Constant?
And the Kemeny constant.
Kemeny constant. Okay, that looks very interesting topic. Okay.
Oh,
so I'm going to hand it over to India.
Good morning, everyone. My name is India, and for my research paper, I looked at applications of graph theory for Markov chains and the Kemeny constant. So the idea is that oftentimes we look at the study of Markov chains through the context of linear algebra. You know, we look at matrices, we solve systems of equations, and so on. But it turns out we can also look at Markov chains through the lens of graph theory. And so graph theory is a more geometric point of view. And so I was interested if there were insights or in how graph theory can complement the study of Markov chains. And the Kemeny constant is a really interesting quantity that's related to the underlying structure of the graph of the Markov chain. All right. So to begin, here's just a few preliminaries that we all know about Markov chains. Okay, so let's see if I can use this pen. All right, so on the left we have our probability transition matrix P and our state transition diagram. And we can really think of our matrix P as, say, representing like the linear algebra point of view for describing a Markov chain. And our state transition diagram, it turns out, represents the graph theory point of view. And we've seen that really our matrix and our state transition diagram, they're really equivalent ways of describing the Markov chain. So once we have our matrix, we can construct our diagram, and vice versa. So they're really equivalent points of, or equivalent representations of the Markov chain. So yeah, so with our P, that's like our linear algebra point of view, and with the state transition diagram, that's really our graph theory point of view, as we'll see. Okay. All right, and so we know that if our Markov chain is irreducible and aperiodic, so that is to say it's ergodic, then we know we're going to have a unique stationary distribution pi. And it turns out that this is an eigenvector for the transition matrix, which is kind of interesting. And also our limiting distribution will exist, and it converges to the stationary distribution. So we know for ergodic chains that the limiting distribution is converges to the stationary distribution. All right, great. Okay, and so our limiting distribution, it really represents the long-term behavior of the Markov chain. And we've seen before that our limiting distribution has to satisfy these conditions. Okay, so we said our stationary distribution represents the long-term behavior of the chain, but we can think of mean first passage times, which again is just the expected number of transitions starting at state I, that the system starts at state I and reaches J for the first time. We can really think of our mean first passage times as representing the short-term behavior of our chain. Okay, so on to graph theory. So maybe you've encountered graph theory before in, say, like a discrete mathematics course, or it actually makes an appearance in the movie Good Will Hunting. So the problem that Will Hunting solves on the blackboard is actually a graph theory problem. And graph theory is interesting because at first glance it appears to be in the domain of like dusty, pure mathematics, but then it pops up in unexpected ways in a lot of different areas. Okay, so let's dive into a little bit of graph theory. Okay, so we can think of like Euler as the father of graph theory, and graph theory is centuries old, and it originated as say one of the solutions to the famous 7 bridges of Königsberg problem. And to solve that problem, Euler represented the bridges and the passageways as a collection of vertices and edges. And that's all a graph is. It's a collection of vertices and edges. Okay. Okay, so there's 2 like main flavors of graphs. So you can have undirected graphs and directed graphs. And for undirected graphs, the edges are really bidirectional. And then for directed graphs, well, then you now have an order. So yeah, so here's undirected graphs and directed. Okay, and if you just imagine like assigning probabilities to the edges of a directed graph, well, what do you have? It's a state transition diagram, basically. So the state transition diagram of a Markov chain is simply a weighted directed graph. And we call a directed graph a digraph. And that's all it is, where the weights are simply the probabilities. Okay, cool. All right, so when we talk about graph theory, we've got paths, we've got circuits, and cycles. But basically, like a cycle is simply a loop, which is a circuit, where no vertices are repeated, except, of course, the endpoint. So here we have a cycle of length 3 from ABC. Okay. All right. So this is an important feature. So we say that a digraph is strongly connected if there's a path between any pair of vertices in the graph. So that is to say, all states communicate with each other. You can reach any state from any other state. And it turns out that this is equivalent to saying that the Markov chain is irreducible. Okay, so over here we have like a strongly connected graph. From any state I can get to any other state. But over here it's not strongly connected. For example, if I start at 2, there's no way I can get to 3. Okay. Yeah, so a strongly connected digraph is going to be equivalent to like an irreducible Markov chain. Okay. All right, the Kemeny constant. Okay, so suppose we play the following game. Say we've got a state transition diagram, and we're given some vertex to start from, like maybe 0 here. And then we just randomly select some other destination vertex to go to. And the question is, well, how many transition steps would you need to get to a randomly selected destination vertex? So maybe we choose 3, or maybe randomly we selected 1, whatever. But we just want to know, what's the expected number of transitions I need to reach that destination state if it's randomly chosen? Okay, and so we could play this game many times. So, you know, maybe we find a value for k0, and here, like, my 0 is just denoting the vertex that I'm starting from. So if I start from 0, then I could find a number from a number for k0. Or if I started at 1, maybe I could find a value for k1, and so on. Okay, and so it turns out, so if you wanted to do this calculation, it's basically like an average of your mean first passage times weighted by your long-term probabilities. So that would be your ki. But the surprising thing is that in 1960, Kemeny and Snell, they showed that your ki's are actually constant. So it turns out it doesn't matter where you start from or where you end up. That value of k, that number, that expected number of transition steps, it turns out it only depends upon the structure of the underlying chain, on how well connected the chain is, which is kind of interesting. So it's just about the geometry of the chain, or the geometry of the digraph, that is to say. Okay, and so the Kemeny constant has several representations. So like in the previous one, like we were given a vertex I, and then we had a random destination point j. But you can also play the game where you randomly select your starting point and also randomly select your destination point. And in any case, it's still going to be this constant number k. Okay, and so a small or a low value of Kemeny's constant, it means that the underlying digraph is in a sense well connected. Like you only need a few steps to reach your destination, so to speak. All right, cool. So in 1960, Kemeny and Snell, they discovered this constant, and it just kind of like fell out of the mathematics. They didn't really have an interpretation for it or anything like that. They weren't really able to explain it. So then 15 years later, one of the authors, Snell, he actually posed this following problem. So he said, a prize is offered for the first person to give an intuitively plausible reason for the above sum to be independent of I. Like people didn't know, well, why is this Kemeny value constant? Okay. So there was a proposed solution by like Peter Doyle in 1983 that was, based on mathematics, but it didn't quite satisfy people. So according to a researcher named Hunter, and this was, just in 2014, so he said that to date, no reasoned argument, apart from some mathematical justifications, has been put forward as a justification as to why this feature of a Markov chain should be constant. So it's still a puzzle. It's still unknown. So, okay, anyway. So why is it constant? We don't know. Okay. So one application of the Kemeny constant is to mixing times. So we know that for ergodic chains, their limiting distribution is going to converge to the stationary distribution. But the question is, how long does that take? How long does the convergence take? And a mixing time is kind of the time it takes for our system to get close, in a sense, to the stationary distribution. Okay, so that's kind of like the general idea. Okay. Okay, yes. So there's a lot of mathematics, but in general, say we denote our time for mixing, so the time that our Markov chain gets close to the stationary distribution, just say we call that t. It turns out that the expected time for mixing, after a lot of mathematics, is in fact your Kemeny constant. So, remarkably, the Kemeny constant gives the expected time for mixing in a Markov chain starting at any state, which is kind of cool. Okay. All right. So some researchers, Boyd and others, they were able to show that, the mixing rate, which is also related to the mixing time, for a Markov chain is determined by the second largest eigenvalue modulus of the transition probability matrix. So, okay, so say we've got our matrix P, and we know it's got eigenvalues. So just say we ordered them, and it turns out that the largest eigenvalue is going to be 1 for our matrix P. And we just ordered them in like non-increasing order. Okay, so, all right, so that would be my second largest there. But basically, the smaller your second largest eigenvalue modulus, or your SLEM, the faster rate of convergence. And so Boyd and other researchers, they wanted to know, okay, so given a stationary distribution and a graph, how can we assign the probabilities to the edges of the graph so that the chain converges in the fastest way possible? Okay, so it turns out you can do that by minimizing this SLEM. Okay, and why on earth would you want to do this? Well, it turns out that the mixing rate is actually important for some applications, like Markov chain Monte Carlo, which is used in like simulation techniques. And so you want to be able to find or bound this mixing time, which is related to our Kemeny constant. Okay. Okay, so he formulated the problem as an optimization problem, and then in turn that can be expressed as a semi-definite program, and they go through an algorithm for how to do this. And they said that, you know, their algorithm works for graphs of, you know, modest size, about 1,000 vertices. But they also think that the same technique can be applied to larger graphs, excuse me, if symmetry groups can be exploited in the underlying graph. So maybe we can use symmetry to help us reduce computational complexity. Okay. So looking at graph theory might be a good idea. Okay. Okay. So the Kemeny constant is full of surprises. So we said that there are many representations to it, and one representation is related to the eigenvalues of the matrix P. So here's one representation of the Kemeny constant, and again we're ordering the eigenvalues. So here when we're doing the sum, we're doing the sum over from the second largest eigenvalue downwards. Okay. All right. And so that's one interesting representation. So, okay. And Hunter also showed that we can find a bound, a lower bound for the Kemeny constant. And so he gave this lower bound. So K of P is greater than or equal to the number of vertices you have minus 1 divided by 2. And it turns out that you're going to get your lowest value of K if P has a special structure. So if your probability transition matrix happens to be the adjacency matrix of a directed n cycle. And we'll see this theme like pop up again and again, that the Kemeny constant is related to the cycle structure of the underlying graph. Okay. All right. So since the Kemeny constant gives the expected time for mixing, a natural question we can ask is, can we characterize the graphs that yield the smaller Kemeny constant? Because if you have a smaller Kemeny constant, you in a sense have optimal behavior in your chain. Okay, and also can we find bounds for it? All right. Okay. So another researcher, Kirkland, he was considering strongly connected digraphs. And he wanted to see, well, what graphs will yield the smallest Kemeny constant value, basically. And again, so I'll just go ahead and read this theorem. So if D is a strongly connected digraph on M vertices, and just say the longest cycle in our graph is denoted by K, then the smallest possible Kemeny value we could have is given by this quantity. Okay, so we've got a lower bound for strongly connected digraphs, and the smallest value of Kemeny will be given by this quantity. Okay, so that's a lower bound for strongly connected digraphs. Okay, so an interesting group of graphs are intercyclic graphs. And so a graph is said to be intercyclic if it has the property that any pair of its cycles intersect. Okay, so in the following graph, we've got several cycles, right? So maybe we have this cycle here, Or, maybe we have like this cycle here. And, there's like several cycles that we could have. But you may notice, you may notice that all cycles go through the vertex 7, right? So this figure would be intercyclic. Okay. And so Kirkland found a bound for the Kemeny constant for intercyclic graphs. And kind of no surprise, this bound was related to the shortest cycle in D. Okay, so this was like an upper bound for the Kemeny constant for these special types of graphs. Okay. All right, so another researcher, Breen, she was trying to minimize the largest mean first passage time in a Markov chain, and she came up with this upper bound. Okay, so the largest mean first passage time we could have is greater than or equal to this quantity here. And she also wanted to know, well, can we characterize the directed graphs that attain this lower bound? So in other words, can we characterize the Markov chains that have the smallest or optimal short-term behavior of the chain? Okay. And she found a group or a set of digraphs that do reach that lower bound, that do have optimal short-term behavior. And they're called Hessenberg cycles. Okay, so to talk about Hessenberg cycles, we have to talk about Hessenberg matrices. So there are these matrices that are almost triangular. So, if you have a square matrix, you're going to have a diagonal, right? Okay, but you also have like a super diagonal and a subdiagonal. And so for an upper Hessenberg matrix, it's going to have 0 entries below that subdiagonal. And then for a lower Hessenberg matrix, it's going to have zeros above that super diagonal. Okay. All right, so here's an example of a Hessenberg cycle. So it turns out if the adjacency matrix of our digraph D is Hessenberg, and after some relabeling of the vertices, there's exactly one arc from vertex M, which is our last one, to vertex 1, then D is called a Hessenberg cycle. So here's an example of a Hessenberg cycle on 6 vertices. And a special feature about Hessenberg cycles is they always have a unique Hamiltonian cycle embedded in the chain. And so a Hamiltonian cycle is just a cycle that goes through every vertex in the chain. Okay, so that's an example of one Hessenberg cycle. Okay, well, why should we care about this, Where do they come up in? So it turns out that there's applications of these Hessenberg cycles. And stochastic Hessenberg matrices can arise as our transition matrices for Markov chains that model certain types of queuing. So there's a queuing system called MG1, and maybe we'll look at that later in the semester. But basically, like customers arrive to the system, they spend a certain amount of time waiting for service, and then they leave after they've been served. Okay, and we've seen like some examples of that with like barbershops and I think like an Italian restaurant and that kind of thing. Okay, so these Hessenberg cycles can be applied to queues such as patients waiting at a doctor's office or vehicles being awaiting service by a mechanic and so on. Okay. And so another researcher, Kirkland, he found another class of graphs with a very specific structure. And his graphs reached a lower bound in this equation, or in this inequality. And it turns out that his graphs also satisfy the conditions that Breen found for minimizing the maximum mean first passage times. Excuse me. So in other words, maybe we can express Breen's results in terms of the Kemeny constant as well. So there might be some interesting connections in there. Okay. So we've seen that the Kemeny constant, it has a strong relationship to the geometry of the associated digraph, especially to its cycle structure. So that's like the secret to the Kemeny constant, is like evaluating the cycles that exist in the underlying digraph. Okay, and for certain groups of graphs, we can find lower and upper bounds. Okay, and still, it's an open question as to why this important feature of the Markov chain should be constant. So we're still awaiting an intuitive justification. And we've seen that Hessenberg cycles have optimal short-term behavior. Okay, and so, we found bounds for very specific classes of Markov chains, but a more comprehensive or general treatment remains open. So can we expand these results to include larger classes of Markov chains? Okay, yeah, all right. Okay, and so the Kemeny constant is really interesting because it can give insight into both the long and short-term behavior of the chain. And I think of it kind of as a bridge between the short-term and long-term behavior of the Markov chain. Okay, that's it. Thank you for listening.
Thank you so much. Thank you, India. Thank you. Great job. Okay, that is very interesting presentation, and we've seen a lot of professional mathematical terminologies, so I can everybody can easily say that what India's background specialty area is. Actually, she's from applied math department, right? Is that right? Okay. Okay. And I also greatly appreciate India spent some time to go over some mathematical terminologies, especially in the graph theory. And also we're going to talk about a little bit about the queuing theory later, probably next week. So, okay, thank you very much, India. Since it's a little bit early, so I prepared another exercise problems for the continuous time Markov chain. Okay? So let me bring it here. Okay, so this is the problem set. So let me give you 2 minutes. Why don't you read through the problem description and try to build up a Markov chain model for that. Okay. Thank you. Okay, so in the first example, we consider a typical gasoline station. And they operate 3 pumps, and the cars, automobiles, arrive at the rate of 1 every 3 minutes. Okay? So, how many 3 minutes do we have within 60 minutes, which is 1 hour? So here, okay, 3 minutes, 3 over 60 hour, right? Which is 1 over 20 hour. So from here, we can see that the arrival rate of the vehicle is 20 per hour. Is that right? Okay, and the average time at the pump is 5 minutes. So the mean service time is 5 minutes. Again, 5 over 60 hour, which is 1 over 12 hour. That is the mean service time, right? Which means, this implies that service rate would be 12 per hour. Is that right? And because of the limited service, no more than 3 cars can wait in the station, in the gasoline station, in addition to 3 cars at the pump. So this implies that the capacity of the gasoline station would be 6, right? Okay. So please make a note. And we assume that a Poisson arrival process and exponential distribution for the time at the pump. Okay, then let's draw a transition diagram for this. So if I say the state number, so that is the number of automobiles that have arrived. Okay. And they are either being served by the pump or waiting in the waiting line. Okay. So in our state definition is the number of automobiles arrived at the gasoline station. So we know that the capacity of this gasoline station is 6, right? So we're going to have 7 different diagrams, right? Starting from 0 to 6. And we're going to put here the arrival rate of the car, of the automobiles, right? So what is the arrival rate? That is 20 per hour, right? Then what is the service rate? Service rate is 12 per hour. Is that right? If there is 1 car, then the arrival rate is still the same, right? 20. If there are 2 cars, what is the service rate? If there are 2 cars in the gasoline station, then they're going to use 2 pumps, right? and each pump will have service rate of 12. So you need to multiply by 2. Is that right? Keep in mind that this gasoline station operates 3 pumps, right? Okay. If there are 2 automobiles, then the arrival rate of the car is still the same, 20. But the service rate will be different, right? Since there are 3 pumps available, if there are 3 automobiles, all 3 of them will be busy with providing service, right? So you need to multiply by 3. And the arrival rate is still the same, 20. Now service rate would be the same as before, because in this gasoline station there are only 3 pumps. Even though there are 4 cars, 4 automobiles in the gasoline station, only 3 of them can be serviced, right? Which means the other one, the 4th one, will be in the waiting line, okay? Same way, the arrival rate is 20, and service rate is 3 times 12. And 20 and 3 times 12. Okay? So this is our transition diagram, Markov chain model of the given problem. Does that make sense? Okay? Okay, now let's move on to the second part. Again, let me give you a couple minutes. Please read through the problem description and try to define the state of system first, and then using the state of the system, you build up the Markov chain model. Okay? Okay, now let's work on this part 2. Okay, this time we consider another small size gasoline station that operates only 1 pump. Okay, so in this case, we assume that cars arrive at the rate of 20 per hour. However, if the pump is already in use, these potential customers may balk, which means drive onto another gasoline station. Okay? because they are busy. Okay? So if there are n cars already at the gasoline station, the arriving car will buck with probability n over 4. Okay? And the n can take 4 different values from 1 to 4. And this value of n becomes 1. I'm sorry, the probability, the buck probability becomes 1 for n is greater than 4. Okay? And the time required to service a car is exponentially distributed with mean 3 minutes. So in this case, what is the service rate? We need to stick to the same unit. So let's use the hour. Okay, so you need to convert 3 minutes to hour, which is 1 over 20 hour, right? Which means service rate should be 20 per hour. Is that right? So let's draw a transition diagram. So if I let each state of the system represents the number of cars arrived at the gasoline station, just like we did in the previous example, then we can draw a transition diagram. 0, 1. So what is this arrival rate? What is this arrival rate? It's 20, right? Over here, 20 per hour. So that's going to be 20 per hour, right? How about the service rate? Is 20, right, per hour. Okay. How about the next arrival rate? If there is one car, what would be the arrival rate? Okay, first, what is the buck rate if there is one car already? 1/4 of the car will live, right? So if we don't consider the buck rate, the arrival rate is 20, right? Since 1/4 of this will go away. So how many cars will arrive? 1 minus 1/4 times 20. Does that make sense? Okay. How about the service rate then? It's the same, right? Since there is only one pump, the service rate is always 20. Okay? It really doesn't matter how many vehicles, how many cars at the gas station. Now you have an idea, right? What is the arrival rate here? 20 times 1 minus 2 over 4, right? Because 50% of these arriving vehicles will leave, right? So the other half will be arrived at the gasoline station. And the service rate is still the same. How about this? 20 times 1 minus 3/4. And the service rate is the same, 20. Okay. How about this arrival rate? If there are already 4 cars at the gasoline station, then the buck rate is 100%, right? Which is true. This is going to be 0, right? Because the buck rate is 100%. The arrival rate would be 0. Okay? So we're not going to include this. So this is the complete transition diagram for our case, continuous time Markov chain model. Okay? Okay, now what if I ask you the expected waiting time of the customer? How do you do that? What is this? So I want you to get the expected waiting time of customers. So this waiting time include at the pump and at the waiting line. Okay, both of them. Okay. Of course, you can differentiate the expected waiting time of the customers in the waiting line. Okay. Or even, I need more space. I don't know how to move the cursor. Okay. Also, what else? We can also ask expected waiting time of the customers at the pump. Okay? So there are 3 different waiting times of the customers. Is that right? So the first one is expected waiting time of the customer in the entire gas station. And the second one would be the waiting time of the customer at the waiting line. And the third one would be the waiting time of the customer at the pump. Okay, while they are being served. Okay, so let's work on this. So in that case, I don't know how to. Let me insert the page. Why it doesn't work? Okay, well, let me redraw the transition diagram so that we're going to work on that from there. There doesn't work. Okay, that's better. So I can redraw the transition diagram. So I can copy here 0, 1, 2, 3, and 4. This goes to 20, 1 minus 1/4, 20, 1 minus 2/4, 20, 1 minus 3/4. And this is 20 all the way, right? So anyway, what is this value? This is 15, right? This is 10, and this is 5. Is that right? Okay, so for us to answer for the question, we need to determine the steady state probability distribution. We can easily see that this is one of the burst test model, right? Number of cars at the gasoline station increased by 1, decreased by 1. Arrival of the car at the gasoline station is independent from the service at the pump, right? So obviously this is the one good example of the burst test process. So we are able to use this streamlined version of the balance equation, which is 20 over 20 plus 20 times 15 over 20, 20, right? 20, 15, 10, 20, 20, 20, right? Multiply those. And then 20, 15, 10, 5. And then 20 to the fourth power. Is that right? So we can see that this is 1 and this is 1, right? This is same. So what is that? There is 75%, right? So 3/4. And then this is can be reduced down to 2. So what is this? 3/8. Is that right? Likewise, 20. Let me just use this. It's better for me. So this goes down to 1, 4, 3, 4. So 32 and 3. Is that right? This is 4. So what is this value? 32, 64 plus 24, 12 plus 2. Is that right? So what is this? 88, 90, 103. Is that right? 32. Which means pi 0 is 32 over 103. Okay. Once you have pi 0, other pi's can be easily obtained. Right? Pi 1 is this first value times pi 0. Pi 2 the second value, 3/4 times pi 0. Pi 3 is third value, 3/8 pi 0. Pi 4 is the last value, 3/32 times pi 0. Right? We've done this many times, right? So I just want to refresh your memory. Okay, now what is the average number of vehicles in the gasoline station? Average number of cars in the gasoline station and the entire system. You remember that is represented by capital R, right? How'd you get it? 0 times pi 0, 1 times pi 1, 2 times pi 2, plus 3 times pi 3 plus 4 times pi 4, right? Which is sum over I equal to 0 to 4 I times pi I. Is that right? I don't know. You can get this value later. And then what is the average arrival rate? That is lambda bar, right? What is your arrival rate? 0 times 20. 1 times, pi 1 times 15. Pi 2 times 10. Pi 3 times 5. Pi 4 times 0. Is that right? So that's how you get lambda. After you get both L and lambda bar, you should be able to get W, which is the average waiting time of the customer. That is the average waiting time of the customers in the gasoline station and the entire system. Okay? So we know the Litter's law, right? Using the Litter's law, W is L over lambda bar, right? Because Litter's law, L equals lambda bar W. Okay, now, what if I ask you the average waiting time of the customers in the waiting line? How do you answer for this? So that is represented by W sub Q. This Q stands for the queuing line, okay? Waiting line. And I got to tell you that just like this, with a small modification, RQ equals lambda bar times WQ. Okay? That works. So now you have an idea, right? In order for you to get WQ, what do you need? You need to get this, RQ. You already have lambda bar from here, right? So what you need is compute RQ. How do you get this? What is RQ then? Compared to R, what is the difference? Subscript Q has been added right now. So compared to R, which stands for the average number of cars in the gasoline station, in the entire system. Here, RQ stands for the average number of cars in the waiting line. Okay? So can you compute that? How many pumps you have? Well, this is not a good example. Probably in the previous example, that will be much clearer. Yeah, that will be better example. This is not a good example, actually. Because in this case, If there is 0 customers, 0 cars, then how'd you get this? Okay, let me get this. So how'd you compute this? RQ. So let's start from here. If there are 4 cars in the gasoline station, then how many cars are waiting in the waiting line? Only 1 of 4 cars are being served, right? Which means 3 other cars are in the waiting line. Is that right? So if there are 4 cars, then 3 of them are in the waiting line. Is that right? If there are 3 cars in the gasoline station, then how many cars are waiting? 2 of them are in the waiting line because there is only 1 pump in this gasoline station, right? So it's going to be 2 times pi 3. If there are 2 cars, then 1 car is being served. The other car is in the waiting line. If there is only 1 car, then there is no cars in the waiting line. So it's going to be 0, right? Of course, if there is no car in the gasoline station, then the car in the waiting line will be 0, right? So if you do this, then you should be able to get RQ. Is that right? And then after that, you should be able to get WQ. Does that make sense? Okay. So in the same way, you should be able to get the average waiting time at the pump. Okay? Okay, I think this is all for today. So this Thursday, we're going to continue on the project presentation, okay? And then next week, we're going to talk about the queuing theory, okay? That's what you are going to do. Thank you very much.